Hello everybody. Today is our last lecture of this particular module. So in this lecture we will summarize whatever we have done in this module, and we will also see how the Boolean expressions would be implemented using gates, and what would be the um, what would be the we we started our logic minimization with an objective of cost optimization. So in this lecture we will also see what is the actual meaning of cost. We have perceived, we started with some notion, and we'll try to elaborate that particular notion of cost. And we'll also see whatever methods we have studied, what is the optimality of those methods, or is there anything better or worse. Okay, so when we started logic optimization, we considered that a Boolean expression is given as an input. And also over the last couple of lectures we have seen that the same Boolean expression or same Boolean function could be expressed in form of multiple functions or multiple expressions, while all of these expressions could be equivalent because they would generate finally same truth table. With this particular idea, since there are multiple options, multiple expressions for the same function, so the optimality idea came into picture. So we would like to represent the whole function in an expression which has a minimal hardware cost. And how have we defined the optimality criteria? How we had defined that a particular expression will lead to a less cost. The cost function in our previous lecture we have treated like two points. One, that the number of product terms in a sum of products, number of product terms should be minimum, and two expressions with same number of products, then the number of literals in each product should be minimum. So with this criteria we can see that whether which expression is less costly or more optimal. Similarly, for product of sums, the number of sum terms should be minimum, and the number of literals in each sum term should also be minimum if the number of sum terms are same. So let us in this optimality criteria we have further assumed that the input is available as both in original form as well as in the complemented form. So let's try to understand what is the meaning of this optimality criteria in terms of a hardware implementation or implementation using logic level gates. Okay, so to understand this we have to see that each product term in a sum of product expression, each product term would lead to one particular AND gate, and the number of literals in that product term would be the number of input in that AND gate. And when we are doing sum of products, so all these product terms would finally be added, so there would be an OR gate in the end, and the input of number of inputs to that OR gate would be equal to the number of product terms. So that means if we are able to understand what is the impact of number of inputs or number of outputs of a gate, then we would be able to understand what would be this optimality criteria. Now when we talk about hardware, in hardware the cost is a vague term. It could lead to multiple of these things, multiple of matrices. So let's say two important matrices for hardware cost is called area and delay. What is area? How much silicon or how much silicon we are going to consume when we implement a particular expression. And delay is end-to-end delay. So let's say all the inputs are available, when the output is available, that would tell us what is the delay. Now, given a particular gate, area depends on how many gates and how many inputs are there in each gate. These two things would be sufficient to know what would be the area. Along with that, it also depends on how many interconnects, how many wires are there, so those also add to the overall area. But in general, the number of gates give us a sufficient idea that what would be the area of a particular chip. Now the second part is delay. So if we know the delay of each gate, then we can also calculate, we can also find out the delay of whole expression or whole logic, whatever we are implementing. So for one particular gate, the delay depends on how many inputs are there, and the output is going to how many other gates. So there is also equivalent terms for number of input of the gate. It's called fan in. Fan in means how many inputs are there, and fan out means a particular output is going to how many other gates as an input. So a typical expression says that your delay, propagation delay of a particular gate depends on almost square of fan in, and it linearly depends on number of outputs. As a generic expression, we can also write it that propagation delay is equal to A1 F in. F in is the number of fan in, or number of inputs, plus A2 into F in square, or in number of inputs square, plus A2 into F out, A3 into F out. So this expression essentially means that my delay would linearly depends on my fan out, or to how many other gates my output is going. It depends squarely proportional to number of inputs. So it essentially means that if my fan in, the number of input to a gate is 4, then with respect to, there is another gate which another, let's say, AND gate, which has 8 inputs. So the delay of 8 input AND gate would be much more than the 4 input AND gates. So this expression, this linear expression, or this linear expression which we have written for propagation delay, is sort of an approximate expression. And A1, A2, A3, these constants are also depends on so many other things, like what technology or how we are designing these gates. Further, because people know that designer who design all these gates, they know that input has a severe impact on the delay, so they also do some things in the design to turn around that. So for example, they change the internal design. Okay, how length, breadth of the transistor is designed, so they change that length and breadth parameters so that delay doesn't increase super linearly. They try to make the impact of this fan in as minimum as possible, but that would also give a side effect in terms of much more increase in the area. So for now we can say that yes, there is an impact of fan in and fan out. Also there are some other factors which would depend on which would help in calculating area and delay. That would be like technology or how designers are designing. Okay, so this information is essentially sufficient for now, that the delay would increase more than linearly or squarely proportional to fan in, and also as the fan out will increase, then also delay would increase. Okay, so and there is also an impact of area. So number of inputs would certainly increase the area, but because transistor sizing get affected as the large fan in the gate would be there, number of inputs increases, so the size sometime also increases, not linearly but super linearly. in case of large fan-in gates. So let's now understand what this particular delay, what is the meaning of this propagation delay. So to understand the propagation delay, let's consider that we have a simple AND gate. Let's say these are the inputs, two inputs and one output. Let us assume that the input is changing, both these inputs are changing at same time. Now the delay or a propagation delay essentially means that the output will not change instantaneously, but it will change after some time. So this whole diagram is called timing diagram, where time is the our x-axis is a time axis, and y-axis, because they are all of them are binary gates, all these gates are taking binary input and outputs. So each input, there would be two levels, one level represents 0, another level would represent 1. So in this timing diagram we can understand that whenever input is changing, output would change after some time. So whatever is this time, the difference when output is available or output changed after change in input is called propagation delay. So this propagation means that there would be some slowness. Whenever input is changing, output will not change instantaneously. Why it will not change instantaneously? So we can say there is some on a very high level we can understand that this is sort of inertia. So we also call it inertial delay, that whatever things are there in rest, they would like to be in rest. So it will take some time for change the output level from 0 to 1 and 1 to 0. And if we want to go in little more detail, so it depends on different technologies. Let's say these gates are implemented using CMOS technology. In CMOS, the output and input both are represented by voltage. So output would change from 0 to 1. So basically whenever output is 1, this 1 voltage, this high voltage, is actually stored in a capacitor. And capacitor is a slow device. Whenever a capacitor, you want to discharge a capacitor from 1 to 0, it would be slowly discharged. And it depends on the resistance and the capacitance, that RL constant, that how much time it will take to get discharged. So that's the actual reason of this propagation delay. It's also called inertial delay. One more thing here, that output will start changing after some time. So let's say there would be some uncertainty for this period. So in this period, sometime it is possible that output goes from 1 0 0 1, but it gets stabilized after some time. So this uncertainty is also there during some period. So we say the latency or a propagation delay is the maximum time after that output will not change, given the input has stabilized. If input has stabilized and output should not change after that time, so that's the propagation delay of a particular gate. Similarly, we can define the propagation delay of a combination of gates. Okay, so the overall this propagation delay, as we have seen in the previous slide also, propagation delay depends on type of gate. So let's say whether it's the AND gate, OR gate, or a XOR gate, NAND gate, NOR gate. So type of gate would certainly define what would be the propagation delay. Partly because propagation delay also depends on what is your truth table. Okay, so practically it also happens that the delay for 1 to 0 or 0 to 1 is different. So let's say my input transition is from 1 to 0 or 0 to 1. So both these input transition may lead to different delays. Similarly, at output also, as I said, this in CMOS technologies it depends on the capacitor. So 1 to 0 would require a different delay rise time, and 0 to 1 would require different rise time. From 1 to 0 the fall time could be different. So this 1 to 0, 0 to 1, this transition may cause different delays. So and of course we said that, for example, this AND gate, if the number of input to this AND gate changes, then also delay will change. If this output, instead of going to one particular gate, it also goes to 10 other different gates, then also a delay may be different. So with all this uncertainty, how do we model a delay and how do we optimize at logic level, or in this where we don't know about fan ins and fan out? So about these technology factors. So what do? We take certain assumptions. Many a times we take the maximum gate delay for analysis. So let's say 0 to 1 and 1 to 0, there are two different delays for the output. So whatever is the maximum, we can take that particular delay as the propagation delay of that particular gate. So other than that, so let's say if different fan ins are there, because fan in has more contribution factor, so we can say there could be different models given for fan in of the gate. So we can say that 2 input AND gate has so much delay, 3 input AND gate has so much of delay. So these kind of things would help us in simplifying these facts. Otherwise life at this logic level estimation or logic level optimization would be much more difficult. Okay, so given this, let us see that our standard 2-level logic, which we has been optimizing for so far, what would be the delay of that, so that we can see how our optimization will work. So let's say we take an example that we have this sum of product expression. So we see that for each product term AB, AC and BC, the number of literals in each product term will dictate how many inputs to AND gate would be there. Similarly, the number of product terms will tell how many inputs would be there for the OR gate. Okay, so in other words, number of product terms will define that how many AND gates are there, and how many literals in each product term will define what is the input. So grossly we can say that if number of product terms are minimized, so that means number of AND gates are minimized, also number of input to my OR gate would be minimized. Further, if I have two expression which has same number of same number of product terms, but in one of the product term the number of inputs are less or number of literals are less, that means that particular AND gate will have less number of inputs. So that means delay of that particular AND gate would be less. So effectively whatever we have defined at a very high level would serve most of the purpose that would define the delay of a 2-level logic. So if we say whatever optimality function we have considered, that would also say that the delay of that particular logic would be lesser than a non-optimal one. Okay, so if I want to see the timing diagram of this circuit, let me assume that all the inputs are will change at the same time. So because the inputs are multiple, so we define it like a hexagon. So some, let's say A, B, C, so some of the input could be high, some of the input could be less, and at a particular time, let's say this particular time, inputs are changing. So because input won't change instantaneously, as output will not change instantaneously, this output will also be input to something, so that will also not change instantaneously. So there would be some kind of a slant in this line. So 0 to 1 there would be some delay. So let's take this whenever the values are at 0.5, let's consider the delay from that particular point. Now inputs are changing. After these inputs, after some time, these T signals will change, and these T signals may start changing at earlier point, but let's say some T1 can change little early, depends on the number of input of these gates. Here input of fan in of all the 3 gates are same. fan out of all of them is also same, so we can assume the delay of all the three AND gate would be same. So T1, T2, T3 will change almost at the same time. But in other expressions, let's say a particular one AND gate has 4 inputs, another AND gate has a 3 inputs or 2 inputs. So the gate which has 4 inputs would give the output after little more time than the gate with a smaller input, a smaller fan in. Okay, so after all of these inputs have changed, then at the second level, f will change after some more delay. The total delay would be the sum of two levels. So there would be delay at first level. All of these things are computed in parallel because all the inputs are available at same time. All the outputs T1, T2, T3 would be available at almost same time. So that delay, I can say the delay at first level, and similarly delay at the second level means when these all of these outputs are available, then my OR gate will start computing and f would be available after another set of delay. This whole delay would be the propagation delay. Now from this method we can also see that if my logic is of two level, means only sum of product or product of sum, that also means that my delay would be optimal. So if number of logic levels will increase, that will also increase the delay of a particular expression. So overall, if I want to calculate the delay in these two stages, I can also say the delay would be the maximum delay of stage 1, because only after that, let's say one AND gate has a 4 inputs or 5 inputs, only after that particular gate has computed the expression, the output of that AND gate, then only OR final output of the OR gate will start changing. So this would depend on maximum delay of stage 1 and the maximum delay of stage 2, that would define the total delay. The other thing also we have to note is that because these inputs may be available at different time, T1, T2, T3, so there would be certain time here in the output when output would be fluctuating. So let's consider that T1, this particular AND gate has 4 inputs, all other has 2 inputs. So because T2 and T3 are available early, so there would be they will change the value of f. So there would be certain value of f. After that T1 will come after some time, and T1 will further change the output of the value of f. So there could be certain transitions. We also sometimes call it, there would be spikes. There would be sometime this f would be 1 and 0, but it will get stabilized when this whole delay would be there. So maximum delay of stage 1 plus maximum delay of stage 2, after this much delay there won't be any change in the output. This also so these spikes of 1 and 0 is also called all glitches at the output. So this also give us one particular lesson, that whatever is the delay of my whole expression, here let's say delay of my expression is equal to maximum delay of stage 1 plus maximum delay of stage 2. So what would happen if my input will change before this whole propagation delay of my expression? It would lead to uncertainty. That means we will never know whether the output is corresponding to the previous change or a new change. So that is why it is always desirable, it is always not only desirable, it is important that input should not change. If we want our output for a particular expression, function or gate, my input should not change before this whole propagation delay, or because before the the delay of this whole function. If input will change, that will cause uncertainty. We don't know what that output is, whether output is corresponding to a previous input or a new input. Okay, so this was about the delay. Now let's also consider the effect of fan-in. Let's say we have a gate which has 4 inputs, AND gate. Now this 4 input AND gate, we know that if we this AND gate distribution law applies over the AND gate, so this 4 input AND gate can also be written as we can let's say this is A, B, C, D, and so we can say A and B could be ANDed, B, C and D could be ANDed, and finally the output of this AND gate can also be ANDed. So these two expressions, these two logic expression or these two gate implementations are actually equivalent. And further, if we say we keep this particular equation in front of us, that propagation delay depends on is the square function of my input and linear function of my output. So because here we assume the output is for both of them is same, so here it would depend on the square function of my input. If that is the case, let's take fan-in as 4. So I can say this propagation delay here would be 4 into A1 plus 16 into A2 plus A3, and here it would be twice, because this is first level, this is second level. Okay, so and because both of these gates are looking equivalent, so we are simply saying that whatever is the delay of this, we multiply it by 2, and delay of one 2 input gate is 2 into A1 plus 4 into A2 plus A3. So we can see from this expression that even for the very small value of A2, propagation delay of this particular gate is lesser than a single stage gate. Okay, so what does it mean? It means that if my number of inputs are large, it seems that it is better that if I break that particular gate into smaller gates with multiple stages. How many stages would be there? So so this multiple levels or multiple stages would be there. How many stages would be there? Let's say if I want to create a stages with all the 2 input gates, the number of stages is going to be log n base 2 of the number of inputs. So let's say if the number of inputs are 8, then 3 stages would be sufficient. In first stage, number of gates would be 4, and then the next stage there would be 2 gates, and the final stage there would be 1 gate. So this way, in 3 stage we would be able to create that particular implementation of 8 input AND gate, and delay wise it's going to be much more efficient. Yes, certainly there could be more area in this particular implementation than this implementation. So that's a trade-off, that if we are focusing on delay, then this multiple stage implementation could be good. So this gives us slightly conflicting vibes, conflicting remarks. So in our first remark we said that 2-level implementation looks like a good implementation because the delay we know is certain, that it's a 2-stage delay of first stage plus delay of second stage. Now we are saying that if there is a gate with large fan-in, then we are forcing that particular gate to be implemented as multiple stage or multiple level implementation for that particular gate. Okay, so what it is done finally, it depends on what is done finally, it depends on how many inputs are there. and sometime because if inputs are exceeding certain number, then it usually get implemented as multiple stage instead of two stage, although it would look like two stage, but finally in the hardware we will implement as multiple stage kits. And we'll see in couple of minutes that there would be other advantages also if we implement it as a multiple stage kit.